Okay, so let's start the second part of my talk. In the first part, we have observed what is the P elastica, and also what is not known and what is not known, and we clarified our goal. And in this second part, I would like to state our main results more precisely. Okay, and the first theorem is about optimal regularity. Okay, and the statement is as follows. Let P is an arbitrary exponent between 1 and infinity, and gamma is a Sobolev W2P curve in the plane, and here L denotes just any positive constant. And we assume that this gamma is an arc-length parameterized P elastica. And so this gamma is not only the P elastica, but up to reparameterization, we assume that this gamma is parameterized by the arc length. So the speed is equal to 1. And then we conclude that this curve gamma has the regularity of Sobolev W31 in general. So by the standard Sobolev embedding, we also have that this gamma has a continuous curvature. So this gamma is of class C2 in general, in particular. Okay, this is the general regularity, and in addition we have a more precise regularity statement depending the exponent P. Okay. And more precisely, the important quantity is 1 over P minus 1, in fact. And the first one is, if this 1 over P minus 1 is an odd integer, then the curve is actually smooth. So it is, so we can differentiate it infinitely many times. And if this 1 over P minus 1 is an even integer, then we have this gamma is of class of this Sobolev class, the W2 plus some integer and infinity. And this notation denotes the standard sailing function. So at least this integer is 3. Okay. And the other case is, if the 1 over P minus 1 is not an integer, then we have this kind of Sobolev regularity. And here we have the same exponent, and this part we have some real number r between this region. Okay. So in these cases, we have regularity depending on the exponent. Okay. And moreover, I also mentioned that if the curvature of the P elastica has no zero point, then the curve is again smooth. So the loss of regularity only occurs at the zero of the curvature. Okay, so this is the first optimal regularity result. And so roughly speaking, actually this optimal regularity can be summarized as the curvature K has the exactly same regularity as this function. This function means, so here we denote the sign of x, the variable x, and here we have a function with exponent 1 over P minus 1 exactly. So, and this, as you can easily imagine, that this function has the shape like this, and in the positive part, the function is exactly x of exponent 1 over P minus 1, and we have a sign change in the minus part. And now you imagine that, so for example, if 1 over p minus 1 is an odd integer, so say 3, then of course we have a smooth curve. So this function is smooth. And actually the corresponding p elastica is smooth. And for other exponents, we have some kind of loss of regularity in this function, and this gamma has the same loss of regularity. Okay. So this is why this 1 over p minus 1 exponent is so important in this statement. Okay. So this is the regularity part. And next, we classify all planar p elasticity. Anyway, so I should mention that if p is equal to 2, this exponent is of course 1, which is an odd integer, so the curve is smooth. So this is compatible with the classical result. Okay. Okay, next we classify all planar p elasticity. And in order to state the classification result, it is convenient to divide the exponent into two cases. And the first case is p is less than or equal to 2. So this case in particular contains the classical case p is equal to 2, the classical elastic case. Okay. Okay, and the statement is as follows: let p is an exponent less than or equal to 2, and gamma is p elastica in R2. Then, up to the natural geometric invariances, namely up to a similar transformation in Euclidean plane, which means translation, rotation, reflection, and dilation, and also up to a reparametrization, this curve p elastica gamma is exactly given by a part of one of the following 5 parameterizations. And the parameterizations are given in the next slide, but here we introduce the terminologies describing those curves. And the first case is a linear p elastica, and this is actually just a straight line. So it's a quite trivial case. And also this case 5 is also almost trivial, which is a circle. Just like a standard circle. And from case 2 to case 4, we have non-trivial curves. And this case 3, we have some kind of special curve, which is called borderline p elastica, and this looks like just an infinite length one loop curve. Okay, so this is a line and this is circle. In this case, we have just one loop. Okay, and the other two cases have some periodic structures. And the first case 2, we have a wave-like p elastica, and in this case we have curves like this or like this. And one important point is that in this case the curvature k may change its sign. And on the other hand, in case 4, orbit-like p elastica, we again have some periodic structure, but it looks like this. So in particular, the curvature doesn't change its sign. So it is positive or negative depending on the choice of the sign. Okay. And also I remarked that in case 1, case 3, and case 5, we have a fixed shape in each case. But in case 2 and case 4, we have a one parameter family of curves actually. So depending on the parameter, the shape, the profile may change. Okay. So this is the first classification theorem, which directly extends the classical case p is equal to 2. Okay. Next, we address the remaining case, which means p is greater than 2. So in terms of the ODE, this case is the degenerate case. Okay. And in this degenerate case, any planar p elastic A is again up to similarity and reparameterization. The curve is given by one of the 5 cases. And case 1, case 2, case 4, case 5 are exactly same as the previous case. But in case 3, we have a different type of solution. So we denote it is 3 prime. And this case 3 prime, we have flat core, so-called flat core P elastica. And this is nothing but corresponding to Watanabe's flat core solutions. Okay, so here is our explicit parameterizations. Okay, and this case 1, we have just a straight segment, and this case 5, we have circle, and in case 2, case 3, and the case 4, we have some non-trivial expressions by using p-elliptic notions. And these p-elliptic notions are important materials in our formulae. And this, I should mention that here we have elliptic integrals, p-elliptic integrals, and these are actually previously introduced by, for example, Takeuchi's generalization, and also these are exactly what are used in Watanabe's paper. So the importance of these functions are already known. So our new findings, the definitions of p-elliptic functions, like this elliptic cosine function or elliptic delta function, p-elliptic delta function, or these amplitude functions. And also here you see the hyperbolic tangent and hyperbolic secant function. These are also defined in our paper. Okay. But anyway, here I don't enter the details of the definitions, but just I would like to give one remark that if p is equal to 2, then all the notions coincide with the classical ones. So by this fact, we can easily see that our formulae quite directly extend the classical results. So just taking p is equal to 2, we can recover all the explicit parameterizations for classical classical elastic A in the plane. Okay. So this is the explicit parameterizations mainly in the first case, I mean theorem 2 case. And in theorem 3, so p is greater than 2, we had the flat core p elastica. And flat core p elastica is defined in this way. This is the parameterization of flat core p elastica, and this is given by some kind of concatenation of some curves. And those curves are respectively given by the segment and some non-trivial shape, which is actually a loop with finite distance of the endpoints. So we can actually continue this curve by just attaching straight lines, and then we can again attach some loop. And like this, we can continue the concatenation procedure to define this flat core P elastica. Okay, and I also remark that this is a trivial line, and here we have a non-trivial parameterization, but this actually coincides with the previous borderline case, at least on the level of notation. And in fact, we have a qualitative difference in the property of hyperbolic second, p hyperbolic second function, in the sense that if p is less than or equal to 2, this p hyperbolic second function has unbounded support, so it is a positive function on R. But if p is less or p is greater than 2, then it has bounded support. So the positive part is a bounded interval, in fact. So in this sense, this loop is some kind of bounded loop, in contrast to the previous case, borderline case. But the parameterization itself is almost the same. Okay, so these are explicit parameterizations. And also here, I show you some numerical plots of the profiles. And this figure shows one parameter, some examples of one parameter family of wave-like P elastic A with the exponent P is equal to 3/2. And here you can see some graphical periodic curve. And if we change the parameter, then the curve deforms into non-graphical shapes. And at one point, you can see some closed curve. And then the curve looks like some kind of periodic loop structure. So we have this kind of wave-like family. And this is actually also same as the classical elastica case. Okay. And here we have borderline elastica, borderline 3/2 elastica. As I said, it is just one loop with infinite length. And here you have orbit-like 3/2 elastic A. And by changing the parameter, then the distances of loops shrink. And by changing the parameters, then it will converge to a circle. And it will, at least formally, it converges to a circle, which is case 5. So in this sense, these families are some kind of continuous family with respect to the parameter. Okay. And also I show you the last numerical example, which describes an example of flat core P elastica with exponent here P is equal to 4. And I remarked that as I repeated, we have non-uniqueness in this family, so the positions of these loops are in a sense arbitrary. So for example, you can move this loop here, or maybe you can reflect this loop here. But the sides of the loops must be same. So this is one important rigidity here. Okay, and these are numerical plots. And here I give some remark about the role of the multiplier lambda. So in the definition of P elastica, we had the multiplier lambda. But in our formulae, the multiplier lambda doesn't appear. But this is just due to our formulae is up to rescaling. So after rescaling, the scaling factor lambda vanished. So this is the reason why the multiplier lambda doesn't appear. But in fact, we also have some relations between lambda and the profiles of P elastic A. and which is just skipped in our formulae. And in particular, one important point is that if the lambda is equal to 0, which is called free P elastica, and this just means that we are considering the critical point of the P bending energy without the fixed length constraint, then the curve must be given by either a straight line or the so-called rectangular P elastica. And so the rectangular elastica is a classical notion, and there is a canonical extension of this notion, which we call rectangular P elastica. And the rectangular P elastica means that it is a unique wave-like P elastica with the property that the curve intersects with the x-axis with right angle. And we can actually say that this kind of curve is unique, and we define it, we call it rectangular P elastica. So in the free P elastica case, we have a very strong geometric rigidity of the curves. And in particular, for example, we can say that there is no closed free P elastica. Okay. So this is one important remark. And now, finally, I give you an example of the application of our classification results. And maybe this would be the most fundamental problem in P elastica theory, which is the classification of closed planar P elasticity. And for the first time, we have completely classified all closed planar P elasticity. And the statement is as follows. And let the exponent P is arbitrary, and gamma, assume that gamma is a closed planar P elastica. And then we can say that this curve gamma is either a circle or the so-called figure-8 P elastica, and possibly multiply covered. Okay. And this figure-8 P elastica is again one example of a wave-like elastica, and it looks like this figure. And the shape depends on the exponent P. And these three examples describes the case that P is equal to 6/5 here, and here P is equal to 2, and here P is equal to 10. So the smaller P yields some kind of thinner figure 8, and if P is large, then the leaf of the figure 8 becomes round. Okay, and this is the classical notion of figure-8 elastica, which has already found by Euler in the 18th century. So this again extends the classical result in the elastica theory to the general exponent P. Okay. Okay, so finally, I briefly explained the main idea of the proof. So I just briefly mentioned the whole picture of the argument. Okay, so first, let gamma be an arcless parameterized P elastica, planar P elastica, and we first proved that by using the weak form of the Euler-Lagrange equation for the vector valued function gamma, we proved that gamma is of class W to infinity at least. So it's a kind of soft regularity. And then, in particular, we can see that the curvature is an infinity scalar function. so that the weak form of the corresponding Euler-Lagrange equation for curvature given by this in an integral form becomes well defined, in the sense that here we have the meaning. So note that if the curvature is merely LP function, then this term doesn't make sense. So ensuring some regularity for K is important to make this weak form well defined. Okay. And moreover, we use some transformation which we call Shioji-Watanabe's transformation, which simply regard this term as a single function W. And thanks to this regularity, this W is again L infinity function. And by using this transformation, we can rewrite this ODE into this form. And here you see that there is no complicated coefficient in the leading order term. So it's a quite simple second order ODE. And by using this form, we can prove that the solution to the weak form of this ODE is actually of class C2, so that any solution is a classical solution to this ODE. Okay. And thanks to this fact that any solution is a classical solution, we can now apply the standard theory in the ODE theory to our problem. And we can actually classify all solutions in terms of the initial value problem to the ODE. Okay. And in fact, in many cases, it turns out that the standard Picard-Lindleff theorem applies, and we can conclude that for a given initial value, there's a unique solution. And these cases correspond to the previous cases 1 to 5. But there exists some case with the degenerate exponent P such that the Picard-Lindleff doesn't apply. And this case is actually corresponding to the Flatko case. But in this case, we have no standard uniqueness, but we still have some kind of rigidity result here by using, by carefully applying the uniqueness theory. And then we can still conclude that this case is given by any Flatko solution, some kind of Flatko solution. So here, up to here, we have classified all the possible solutions to the ODE. And finally, so after somewhat independently introducing our p-elliptic functions, we show that all the initial values in this problem can be attained by some solutions given in terms of our p-elliptic functions. So this way, we assert that any solution is represented by elliptic function, p-elliptic function. And by using this representation, we can obtain the full explicit formulae of all planar p-elastic. And also, the optimal regularity is obtained by investigating precisely the regularity of p-elliptic functions, because the curvature of any p-elastica is now shown to be exactly given by p-elliptic functions. So the regularity are directly related. Okay. So that's all of my talk, and this is a summary. In this talk, we have classified all planar p-elastic A and obtained explicit parameterization and optimal regularity. And also, as an application, we have classified free elastic A and also closed p-elastic A. These are direct applications of our classification results. So, and we hope that there are also many applications to deduce more precise properties about involving p-elastic curves or the p-bending energy. Okay. And there are many future directions in this field. So, for example, boundary value problems are in general not solved, or the stability of p-elastic A are completely not known at this moment. And also we are interested in some geometric inequalities and other interesting point is that for p-elastic flows, there are some convergence results which are obtained quite recently, but the topology, the optimal topology of the convergence of p-elastic flows is not known. And maybe our optimal regularity result gives some good information about the goal of the convergence topology. And also we have, in this talk, we have only considered planar curves, but of course spatial curves or more are quite interesting objects to study. And also we have only considered Euclidean plane or Euclidean space, maybe here, but p-elastic curves in curved spaces are also important topics to study, I think. Okay, so that's the end of my talk. Thank you very much for your kind attention.